start periodic properties part 2. Crystal or metallic radii. In a metal crystal, we can think of the atoms arranged as a set of touching spheres. In fact, a large number of atoms are closely packed. These are held together by means of metallic bonds. The bonding in metals is not fully understood compared in bonding in ionic and covalent compounds. The metallic radius may be defined as one half of the distance between the nuclei of two adjacent atoms in a metal crystal. The internuclear distance between the nearest neighboring atoms in a metallic crystal can be determined by X-ray diffraction. Thus, when we have the distance between the two nearest atoms, we get the metallic radius of the atom. R metallic is equals to internuclear distance between two adjacent atoms in a crystal by 2. Alkali metals from well-defined metallic crystals. The alkali metal exists as diatomic molecules in the vapor state. The metallic bond is longer than covalent bond. It means metal atoms in a metallic crystal are not as close to each other as in covalent bond. Ionization energy. In order to promote an electron in an atom from one energy level to next higher energy level, some energy must be supplied. If enough energy is available, the electron can be removed and a cation with unipositive charge is formed. The amount of energy needed to remove the least tightly bound electron from a mole of gaseous atoms is called ionization energy. The process can be represented as M gives M plus electron negative. Ionization energy is measured conventionally in kilojoule per mole. It is possible to remove more than one electron from some of the atom. In such cases, the process can be represented as M gives M plus electron negative, that is E1. M positive gives M double positive plus electron, that is E2. M2 positive gives M2 positive plus electron, E3, where E1, E2, E3 are the amount of energy that are needed to pull the electron one by one and are known as first, second, and third ionization energies respectively. Ionization energies depend upon several factors which are given below. Size of the atom, charge on the nucleus, screening effect of inner electrons, penetration effect of the electrons. Let us discuss these in order to appreciate fully the concept of ionization energy. Size of the atom. The ionization energy depends upon the attractive force with which the outermost electron is held by the nucleus. This in turn depends upon the size of the atom, because the attractive force between the outermost electrons and the nucleus is inversely proportional to the distance between them. Thus, in a small atom, the electrons are tightly held, whereas in a large atom, the electrons are less strongly held. Thus, the ionization energy decreases as the size of atom increases. Second, that is nuclear charge. With the increase in nuclear charge, the force of attraction between the nucleus and the outermost electrons increases. Therefore, more energy is required to remove the outermost electrons. As a result, the ionization energy increases with the increase in nuclear charge. Screening effect. In atoms with more than one electron, each electron repels every other electron and is also repelled by every other electron. The attractive force that each electron feels from the nucleus is affected by all other electrons in the atom. In addition, the inner electrons screen or shield the outer electrons from the positive charge of the nucleus. As a result, the effective nuclear charge, that is the charge actually felt by outer electrons, is less than the actual nuclear charge. Therefore, the ionization energy will decrease. Thus, increase in the number of electrons will decrease the ionization energy. Penetration effect of the nucleus. In case of a multi-electron system, the electrons in the s orbitals penetrate to the nucleus more than p orbitals. It means that s electrons experience more attractive force of the nucleus than p electrons of the same shell. As a result, s electrons are more tight held by the nucleus than the p electrons. Thus, the ionization energy of atoms possessing l electrons will be more than those of p orbitals of same shell. The values of the first ionization energies depend upon the combination of effective nuclear charge, atomic radius, and electronic configuration. It is important to note that elements with the lowest energies are in the lower left corner of the periodic table. Elements with the low ionization energies lose electrons relatively easily and form cations. They are called reactive metals. A careful inspection reveals that electrons with high ionization energies are in the upper right corner of the periodic table. These are all non-metals. Elements with high ionization energy do not lose electrons easily. We can say that the ionization energies are periodic function of atomic number. The elements of group 18, the noble gases, have the highest first ionization energy of all groups and stand at the peak of the plot. Helium, the noble gas with the smallest atomic radius, has the highest first ionization energy of all the elements. It is high ionization energies of the noble gas that suggest the extraordinary stable electronic configuration of these gases. Let us now turn to the troughs in the plot where the ionization energies are the lowest. These elements are members of group 1. The outermost electrons of lithium, sodium, potassium, rubidium, cesium are all s electrons. It is clear from the graph that the single s electrons requires relatively little energy for removal of outermost electrons compared with the needed to remove the other electrons. Cesium with the largest atomic radius has the lowest first ionization energy. This is because s electrons are in new shell farther from the nucleus than